Hello, this is Dr. Amudapriya, Associate Professor of EEE, Rohini College of Engineering and Technology, Palkula. And here we are discussing about the transmission and distribution subject for the regulation 2021. And the discussion is about the power factor and heating of cables. When we are considering the underground cables, the temperature rise of a body will tend to, it depends upon the rate of generation and dissipation of heat. If the rate of generation is greater than that of the dissipation rate, obviously the temperature goes on rising and vice versa. In a UG cable, sources of heat generation, that it may be due to core loss or copper loss in the core and the dielectric loss and sheath losses. The heat is dissipated through the dielectric to the ground and finally to the atmosphere. So core loss, as we know, it is nothing but the conductor, the resistance of the conductor and the ambient temperature when it is known, we can calculate the resistance let us consider an operating temperature of 65 degrees centigrade and with an ambient temperature of 20 degrees centigrade. Earlier we have discussed in further lectures that R value, the resistance value is R 65 is equal to R20 into 1 plus alpha T, where alpha is the temperature coefficient of the conductor material. Obviously, the temperature is nothing but 65 degree minus 25 degree, it is 45 degrees. Since the effective area of cross section of the cable is smaller than the actual physical section, the effective resistance will be larger. Normally, if you see that the effect of stranding on the resistance is obtained by multiplying the resistance which is being calculated according to the length of the central strand. We used to multiply it with a factor of 1.02. So, while considering the core losses like I square or loss, we know that I is the current carried by the cable. Next is the dielectric loss. So, while considering a dielectric, we can consider the modeling of the dielectric material to be a resistance and capacitance in parallel to each other. So obviously two currents will be flowing, IR and IC, and we know how IR and IC will be with respect to the voltage value. IR will be in phase with the voltage, but IC will be leading the voltage by means of 90 degrees. So when we are having the resultant current of I, it may consist of IC and V by R. So this is how we calculate the power value. The P is equal to V square omega C into tan delta. Delta is nothing but the dielectric loss angle and omega is the power supply frequency. Since delta is normally very small, we used to consider tan delta as del itself. So P is equal to V square omega C del watts is an obvious equation for calculating the dielectric losses. From this, we know phi is equal to 90 minus del. So cos phi is equal to cos 90 minus del, which is equal to sin del. So this implies that the power factor of a dielectric is a function of the temperature of the dielectric and also depends upon the voltage stress to which the dielectric is stressed. And next, while considering the variation of dielectric power factor with respect to temperature, we can see from the graph when the temperature increases, the power factor is getting decreased. So somewhere else between the points between 30 degrees centigrade to 60 degrees centigrade, we have a minimum power factor, and obviously after that the power factor shoots out. This is the case. The temperature increases around the operating temperature and the dielectric losses also increases and hence larger heat generation occurs. It will be increasing the temperature gradient between the cable and the atmosphere, thereby heat dissipation will be occurring. If this rate of heat dissipation is less than the heat generation, the dielectric overheats and it fails electrically. This is known as thermal instability, and the action taken to reduce the loss angle generally, it will flatten and reduces the thermal instability. And while considering the variation of dielectric power factor with respect to voltage, in solid type of cables, when the stresses are high, dielectric loss does not vary directly as square of the voltage. The losses are more due to the ionization at weak points in the insulation. As a result, there is an increase in the dielectric power factor. We can see this as dielectric stress increases. Normally, the power factor will be a constant and it doesn't react, and after that it will be progressing in order to break down the voids. and obviously the whole insulation will be breaking down. Next is the sheath losses. While considering the sheath losses, when single core cables are being used for AC transmission, the current flowing through the core gives rise to a pulsating magnetic field, which when linked with the sheath obviously induces voltage in it. This induced voltage will set up a current under these conditions in the sheath, and this results in the sheath losses. Normally, if we consider lambda as a ratio of sheath loss to the conductor loss, the equivalent AC resistances R equivalent is equal to R into 1 plus alpha. Here R is nothing but the resistance of the core of the cable, and according to Cramp and Calder rule, the sheath currents can be divided into two types, namely sheath eddy currents and the sheath circuit currents. Eddy currents which flow along the surface, and the circuit currents is nothing but which will flow from one cable to the sheath of the another cable. The first type of currents will flow through the sheath when the sheaths of the two cables are not connected at both the ends, and when they are connected only at one end, because the currents do not find a closed path through the sheaths of the two cables. But the second type is that they are electrically connected at both the ends and there is a bonding of cables. So the voltage V is equal to omega M into I. M is nothing but the mutual inductance between the core cable and the sheath. Mutual inductance, as we know, the flux due to I in one conductor extends up to the center of the other conductor, and the flux lines that enclose both the core and the sheath of the same cable will extend from the center of the other cable to the mean radius of the sheath of the cable. So we can see from this diagram, and any flux line between the R and the RM values, it will be connected only to the conductor and not the sheath. So obviously M is equal to 2 into 10 raised to minus 7 natural logarithm of D by Rm value. Therefore Vs is equal to omega Mi. When we substitute, we get this equation. So if it is 2 Vs, if the sheaths are bonded at the center, then the voltage between the two sheaths at the far end will be 2 Vs. Suppose in case of a short circuit, the currents I are of larger magnitude than the voltages, and this may push up the voltage, high voltage between the sheaths, and the sheaths are not being bonded. These high voltages may result in sparking between the sheaths and then pitting the surface of the sheaths of the cable. So we can have eddy current losses to be I square into 3 omega square by Rs into Rm by D the whole square into 10 raised to minus 18 watts per centimeter per phase. You can see these losses are usually negligible, as they form only about 2% of the core losses. Thank you.